What if I told you the world around us, everything we see and touch, might not be as solid as it seems? Picture reality as a grand illusion, a shimmering mirage built on something far stranger, an invisible, ever-shifting web of quantum fields. These fields aren't just the backdrop of the universe, they are the universe, humming with energy even in the emptiest corners of space. Imagine dipping your hand into a cosmic soup where particles flicker in and out of existence, where the vacuum itself crackles with hidden potential. This isn't science fiction, it's the cutting edge of physics, and it's about to turn everything you thought you knew on its head. Now, think of the universe not as a collection of distant stars and planets, but as a single, vibrating tapestry. Every atom, every beam of light, every whisper of gravity is just a ripple in these quantum fields. They're like invisible oceans stretching endlessly in all directions, and we're floating on their surface without even realizing it. But here's where it gets wild. What if these fields hold secrets that could rewrite the rules of reality itself? What if time, space, even the very fabric of cause and effect are just side effects of something deeper? That's exactly what we're diving into today, 30 mind-bending theories that push the boundaries of what's possible. From the idea that our universe might be a hologram projected from the edge of space, to the notion that every decision you make spins off parallel worlds, these aren't just thought experiments. They're clues to the universe's greatest mysteries waiting to be unraveled. So buckle up. By the end of this journey, you might never look at the night sky or even your own reflection the same way again. Let's start with a theory so radical it redefines reality itself: the holographic principle. Imagine your entire life, every tree, mountain, even the vastness of space isn't truly three-dimensional. Instead, it's all a projection, like a cosmic movie screen, encoded on a distant two-dimensional surface at the edge of the universe. This isn't just a wild guess. It comes straight from the work of physicists like Leonard Susskind, who realized something baffling about black holes. When matter falls into one, the information it contains doesn't just vanish. It gets smeared across the black hole's event horizon, almost like a fingerprint pressed onto its surface. That led to a jaw-dropping idea. What if all information in the universe works this way? Here's where string theory adds another layer. In this framework, the universe might be like a hologram where the real action happens on a flat, distant boundary, and what we experience is just a shadow, a three-dimensional illusion. Think of it like watching a movie. The images seem deep and lifelike, but they're really just patterns of light on a flat screen. The holographic principle suggests our reality operates the same way, with every event, every particle traced back to a two-dimensional code. But the most mind-blowing part, this implies there's a fundamental limit to how much information can exist in any given space, much like pixels on your phone screen. Pack in too much detail and the universe literally runs out of storage. That's why some physicists argue even empty space isn't truly empty. It's a seething network of tiny, indivisible bits of information, constantly updating like the universe's own operating system. If this theory holds, it means everything, your thoughts, the stars, even time itself, might just be data on the cosmic hard drive. But if reality is a hologram, what's it made of? Dive deeper past the illusion, and you'll hit something even stranger: quantum foam. Picture spacetime not as a smooth, invisible fabric, but as a churning ocean, frothing with unimaginably tiny bubbles popping in and out of existence. At scales so small they make atoms look like planets, the universe isn't serene. It's chaos. This wild idea comes from physicist John Wheeler, who realized that at the Planck length, a distance so tiny it's a billion trillion times smaller than an atom, space itself might not be continuous. Instead, it could be a seething, turbulent foam, constantly bubbling with pairs of virtual particles that flash into existence for mere fractions of a second before annihilating each other. Think of it like a pot of water on the brink of boiling. Even before bubbles rise, tiny pockets of steam form and collapse in a frenzied dance. Quantum foam suggests spacetime does the same thing, with particles and energy appearing from nothing, just long enough to obey the uncertainty principle, then vanishing again. This isn't just theoretical, it directly challenges Einstein's vision of gravity as the bending of smooth spacetime. If the fabric of reality is foamy, then gravity might work differently at these minuscule scales, warping in unpredictable ways. And here's where it gets mind-bending. Some scientists suspect we might actually see quantum foam's fingerprints in the distant cosmos. When gamma rays, the universe's most energetic light, travel billions of years to reach us, the foam's turbulence could leave subtle marks on their journey, like ripples distorting a signal. Experiments are already hunting for these tiny anomalies, and if we find them, it would mean spacetime isn't just bumpy, it's fundamentally pixelated, like static on an old TV screen. So the next time you gaze at the night sky, remember, the smooth black expanse above you might actually be a storm of quantum uncertainty, churning just beneath the surface of perception. Now, let's talk about a theory so unsettling it could rewrite reality in an instant vacuum decay. Picture the universe resting on a fragile ledge, not quite at its lowest energy state, but perched in a precarious metastable false vacuum. One tiny nudge, one quantum fluctuation in the wrong place, and everything we know could vanish in a blink. Here's how it works. The Higgs field, which gives particles their mass, might not be sitting in its most stable configuration. Like a marble balanced on the edge of a bowl, it's holding steady for now, but if it rolls into the true vacuum state, it would unleash a catastrophe beyond imagination. A bubble of true vacuum could form without warning, perhaps triggered by a high-energy collision in a particle accelerator or even a random quantum event in deep space. This bubble would expand at the speed of light, rewriting the laws of physics as it goes. One moment, atoms, stars, and life exist as we know them. The next, the universe inside the bubble operates by entirely new rules. Chemistry, light, even the forces holding your body together would cease to function in the way they do now. There'd be no warning, no time to react. The shockwave would hit at light speed, erasing existence as we understand it before we could even blink. The scary part, we might already be dancing on the edge. Experiments at CERN probing the Higgs boson's properties could, in theory, reveal whether our vacuum is truly stable or teetering on collapse. Some calculations suggest we're alarmingly close to the tipping point, a reality so fragile that even the energy of a distant supernova might be enough to knock the Higgs field out of its false vacuum. And yet, if the bubble hasn't formed in 14 billion years, maybe the universe is more resilient than we fear. Or maybe we're just astronomically lucky so far. But here's a twist. If vacuum decay did happen, we'd never see it coming. The bubble's leading edge would move at light speed, meaning the destruction would arrive at the exact same moment we detected it. No distant warning flashes, no cosmic countdown, just silence. Yet some theorists argue this might not be the end. A new universe with different physical constants could emerge from the wreckage, one where life might take root under entirely unfamiliar laws. So while vacuum decay sounds like doomsday, it could also be the ultimate cosmic reset button, a terrifying yet awe-inspiring reminder of how delicate our reality truly is. What if randomness isn't the true heart of quantum mechanics? That's the bold claim of pilot wave theory, a radical alternative to the mainstream Copenhagen interpretation. While most physicists accept that particles exist in fuzzy probability clouds until measured, pilot wave theory dares to suggest there's an invisible hand guiding every quantum dance, a deterministic blueprint hidden beneath the chaos. This idea traces back to David Bohm, a physicist who refused to believe the universe operated on pure chance. Instead, he proposed that every particle has a definite position at all times, steered by a mysterious pilot wave that orchestrates its path. The beauty of this theory lies in its simplicity. Picture a tiny boat floating on a lake, not drifting aimlessly, but pulled by unseen currents beneath the surface. That's how particles behave in Bohm's universe. No dice rolls, no quantum weirdness, just hidden forces dictating their every move. Even the famous double-slit experiment, where particles seem to act as both waves and particles, gets a clean explanation. The pilot wave creates interference patterns in advance, guiding particles like clockwork to create the illusion of wave-like behavior. But here's where it gets tangible. Modern experiments with bouncing droplets, tiny beads of fluid vibrating on a liquid surface, mimic this behavior eerily well. These droplets, propelled by their own waves, recreate quantum effects like tunneling and quantized orbits without any randomness at all. It's as if nature is whispering that Bohm might have been onto something. So why isn't pilot wave theory the law of the land? For many physicists, its biggest flaw isn't math or evidence, it's philosophy. The theory demands a level of determinism that feels out of step with modern quantum thinking, where probability reigns supreme. Worse, it introduces non-locality on steroids. Particles instantly influence each other across vast distances, a feature Einstein famously called spooky. And while the math checks out, some argue it's less elegant than the Copenhagen approach, adding hidden layers without new predictive power. Yet, pilot wave theory lingers like a ghost at the feast of quantum physics, a reminder that maybe, just maybe, the universe prefers order over chaos. Whether it's a forgotten relic or a future revolution waiting to happen, one thing's certain. It forces us to question whether randomness is real or just a placeholder for deeper laws we've yet to uncover. Ever wondered why the quantum world feels so alien compared to our everyday reality? Why atoms can exist in multiple states at once while cats or coffee cups seem stubbornly definite? That's the puzzle quantum Darwinism aims to solve. Proposed by physicist Wojciech, this theory suggests there's no mystical observer collapsing quantum state, just the relentless sieve of the environment itself. Imagine Schrödinger's infamous cat, neither dead nor alive, but constantly bombarded by photons, air molecules, even cosmic rays. Each interaction acts like a tiny vote, gradually amplifying one outcome while suppressing others until only the fittest state survives. Think of it like a game of quantum telephone. A particle starts in superposition, say, spinning both clockwise and counterclockwise, but every time it interacts with its surroundings, information about its state leaks into the environment. Photons scatter off it, air molecules bump into it, and each collision leaves a microscopic imprint. Over time, countless copies of one particular state, like clockwise spin, spread through the environment while the alternative fades into obscurity. By the time you look, the universe has already voted. The particle state appears classical because its quantum weirdness has been drowned out by a chorus of environmental echoes. This isn't just philosophy. Lab experiments with entangled particles show how decoherence, the loss of quantum coherence due to environmental noise, mirrors this natural selection process. When quantum systems interact with their surroundings, their superpositions unravel, leaving behind the robust classical states we observe. It's as if reality has a built-in editor, trimming away the improbable branches of the quantum multiverse until only the most stable versions remain. But quantum Darwinism goes further. It suggests that the states we perceive as real are simply the ones best at replicating themselves across the environment. Like genes surviving natural selection, only the most resilient quantum states persist long enough for us to notice. A chair isn't in a definite position because some conscious observer wills it so. It's because its location has been copied countless times by photons bouncing off it, air molecules nudging it, and dust settling on its surface. The universe, in this view, isn't passively observed. It's actively broadcasting its classical reality through endless environmental interactions. So next time you flip a light switch or catch a ball, remember, The solid, predictable world around you might just be the quantum equivalent of a viral trend, a state so adept at replicating itself that it's become the only version of reality you'll ever see. And the eerie quantum underpinnings, they're still there, humming quietly beneath the surface, filtered out by the ruthless democracy of the cosmos. What if the quantum fields humming beneath reality aren't just the universe's foundation, but the code of a simulation? This is the heart of the simulation argument, a theory that ties the weirdness of quantum physics to something even stranger. The idea that we might be living inside an ancestor simulation, a hyper-advanced civilization's recreation of history. Philosopher Nick Bostrom framed it as a trilemma, three unsettling possibilities. Either civilizations never reach the tech to run such simulations, they choose not to, or we're almost certainly inside one right now. And quantum mechanics might hold the clues. Take the double-slit experiment where particles act like waves until you measure them, collapsing into definite states. In a simulated universe, this could be a processing shortcut. Rendering every particle's exact position in real time would require unimaginable computing power. But if the system only calculates precise locations when observed, like a video game loading graphics only when a player looks, it saves resources. The wave function isn't a fundamental mystery. It's the simulation's way of avoiding overload, like a cosmic render distance setting. Even quantum indeterminacy, where particles lack definite properties until measured, fits this picture. Uncertainty isn't a feature of reality, it's a buffer, masking the limits of the system running our universe. Here's where it gets spine-tingling. Glitches in quantum behavior, like particles teleporting through barriers, quantum tunneling, or entangling across galaxies, might be artifacts of the simulation's code. Think of a game lagging when too many NPCs interact. Our universe's lag could be the probabilistic blur of quantum states. Even the Planck length, the smallest possible unit of space, might be the pixel size of the simulation's resolution. And just as a computer can't process infinite decimals, rounding off numbers at some point, quantum fields might discretize energy because the simulation has finite precision. But the most haunting evidence, the universe's mathematical elegance. The laws of physics follow precise equations, as if written in some cosmic programming language. From the Fibonacci sequence in sunflowers to the golden ratio in galaxies, nature's patterns feel designed, optimized. Could that be because they were designed not by a deity, but by engineers with unfathomable tech? Of course, this isn't proof. Critics argue the simulation theory is unfalsifiable, a modern myth dressed in sci-fi allure. Yet it forces a chilling question. If we ever did find proof, would the simulators let us know? Or would they patch the discovery like a bug, resetting the simulation before we cracked the code? Either way, the theory turns quantum fields into something far more unsettling. Not just the fabric of reality, but the lines of a script we're all acting out, unaware the stage might be digital. There's a theory that suggests our universe isn't just expanding, it's multiplying, endlessly birthing new realities like bubbles in a boiling cosmic kettle. This is eternal inflation, where the fabric of spacetime isn't merely stretching but constantly giving rise to pocket universes, each with its own unique set of physical laws. Imagine space as an infinite froth where every bubble inflates into a full-fledged cosmos, some with gravity stronger than ours, others with no stars at all, even some where time flows backward. Our universe, then, isn't special, it's just one of countless accidents in an unending explosion of creation. What makes this idea so compelling is how it tackles one of cosmology's biggest mysteries, fine-tuning. The constants of nature, like the strength of gravity or the mass of an electron, appear perfectly calibrated for life to exist. Tweak them even slightly, and atoms wouldn't form, stars wouldn't ignite, and the universe would be barren. Eternal inflation offers an elegant escape from this puzzle. If infinite universes exist with every possible configuration of physics, of course we'd find ourselves in one where conditions allow life. The rest, they're out there, empty or bizarre, invisible to us but no less real. But there's a catch. While eternal inflation neatly explains fine-tuning, it also raises a haunting question. How do we test a theory where every possible universe exists? Without a way to peer beyond our cosmic bubble, it risks becoming untestable, a beautiful idea trapped in the realm of philosophy. Some physicists argue that traces of collisions between our universe and others might linger in the cosmic microwave background, subtle wrinkles in the afterglow of the Big Bang. Others look for anomalies in particle behavior that hint at interactions with parallel brains in higher dimensional space. So far, no smoking gun. Yet even without proof, eternal inflation reshapes how we see existence. It turns the multiverse from sci-fi speculation into a plausible consequence of quantum field dynamics, where the vacuum's energy doesn't just fade, it reproduces. And if true, it means the greatest cosmic tragedies, entire universes born dead, laws of physics hostile to life aren't failures. They're inevitable byproducts of a reality too vast to care. We might never visit these other worlds, but their existence would mean ours isn't a miracle. It's a statistical certainty, one lottery ticket in an infinite stack where every possible outcome, no matter how wild, gets drawn somewhere. What if consciousness isn't just a passive observer of reality, but the very force that shapes it? This is the provocative heart of the orchestrated objective reduction theory, or ORCH, proposed by physicist Roger Penrose and anesthesiologist Stuart Hameroff. They argue that the mysterious collapse of the quantum wave function, the moment particles choose a definite state, doesn't happen randomly or through environmental noise. Instead, it's guided by structures deep inside our brain cells, microtubules. These tiny protein filaments found in neurons might be quantum processors far more sophisticated than we ever imagined. Picture microtubules as the universe's smallest orchestra conductors. According to Penrose and Hameroff, these structures can harness quantum vibrations, maintaining superpositions of states long enough for gravity, yes, gravity, to step in and trigger collapse. The idea is that at impossibly tiny scales, spacetime isn't smooth. It's lumpy, warped by the mass of particles in superposition. When this gravitational strain becomes too much, the system reaches a threshold and chooses a state. And here's the kicker: this collapse isn't just physics, it's experience. Each orchestrated reduction is a moment of conscious awareness, a flicker of subjective reality emerging from the quantum fog. But how could something as delicate as quantum coherence survive in the warm, wet chaos of the brain? Critics pounce on this, pointing out that quantum states in lab settings require near-perfect isolation, supercooled vacuums, shielded from all noise. The brain, by contrast, is a bustling molecular marketplace, yet Penrose and Hameroff counter that microtubules might be uniquely suited to protect quantum information. Their symmetrical lattice structures could act like Faraday cages for quantum vibrations, shielding them long enough to influence neural processes. Some studies even suggest anesthetic gases, which switch off consciousness, work by disrupting these quantum vibrations in microtubules, a tantalizing clue. The implications are staggering. If ORCH is correct, consciousness isn't an emergent property of classical physics, like a hurricane arising from air currents. It's a fundamental feature of the universe, woven into the fabric of reality itself. Free will wouldn't be an illusion, it'd be quantum choice crystallizing in our neurons. Near-death experiences, perhaps moments when quantum states in microtubules persist even after clinical death, explaining lucid memories of the dying brain. Even creativity and intuition might stem from these quantum computations, tapping into possibilities beyond classical logic. Of course, the theory has fierce detractors. Many physicists argue that gravity's role at quantum scales is negligible, and no evidence yet proves microtubules function as quantum computers. Others dismiss ORCH as wishful thinking, a desperate attempt to place consciousness at the center of physics. But whether it's right or wrong, the theory forces us to confront a profound question. If the universe only takes definite shape when observed, what does that say about the observer? Are we merely bystanders or participants sculpting reality with every thought? Either way, or turns the mystery of consciousness into something far grander. A cosmic dance between mind and matter, where the observer might just be the most important player of all. Imagine holding a glowing hologram in your hand, a flat, two-dimensional image that somehow contains all the information needed to reconstruct a three-dimensional object. Now stretch that idea to cosmic proportions, and you've got the AD/CFT correspondence, a theory so powerful it bridges the chasm between quantum mechanics and gravity. At its core is physicist Juan Maldacén's bombshell discovery. A quantum field theory operating in a lower dimensional space can perfectly describe gravity in a higher dimensional universe. It's like finding the user manual for a hyperdimensional engine written entirely in binary code. To grasp how radical this is, picture a black hole, a cosmic vault where gravity is so intense even light can't escape. According to general relativity, anything that falls in is lost forever, its information obliterated. But quantum mechanics insists information can't vanish, it must be preserved. This is the black hole information paradox, a clash between our two greatest theories of reality. Enter AD/CFT, which suggests the information isn't destroyed, it's encoded on the black hole's event horizon like data etched onto a cosmic DVD. The three-dimensional chaos inside the black hole is mirrored perfectly by a two-dimensional quantum field theory on its surface, where gravity doesn't even exist. Here's where it gets mind-bending. The AD/S in the name refers to anti-de Sitter space, a hypothetical universe with negative curvature, like a saddle stretching infinitely in all directions. In this exotic geometry, the boundary, the edge of spacetime, behaves like a quantum field theory, the CFT, or conformal field theory. The holographic magic happens because equations governing particles on the boundary's flat surface exactly match those describing gravity in the warped interior. It's as if the universe is running a simulation where the code is simpler than the graphics. But why does this matter beyond theoretical fireworks? For one, it suggests gravity might not be a fundamental force at all, just an emergent illusion, like temperature arising from the motion of atoms. String theorists seized on this idea, recognizing that AD/CFT could unlock quantum gravity's secrets without wrestling with infinitely complex equations. Even practical applications loom. Some researchers speculate the correspondence could revolutionize quantum computing by revealing how to store information in lower dimensional systems. Yet the most profound implication is philosophical. If our own universe operates like a hologram, with bulk physics encoded on some distant boundary, then reality isn't just stranger than we imagine. It's stranger than we can imagine. Maldacén's duality doesn't just solve paradoxes, it whispers that the universe might be the ultimate puzzle, written in layers we're only beginning to peel back. And somewhere in that nested code could lie the keys to everything, from the birth of spacetime to the fate of information itself. What if spacetime, the very stage on which the universe plays out, isn't fundamental at all? Think of it less as the foundation of reality and more like ice forming on a lake's surface, a temporary structure emerging from something deeper. This is the radical premise of emergent spacetime, a theory that suggests the fabric of the cosmos might be woven from quantum entanglement, threads of information linking particles across vast distances. Picture the universe as a cosmic blockchain, where every transaction, every interaction between particles creates a new link in the chain, and spacetime is just the ledger recording those connections. The math behind this idea is as elegant as it is mind-bending. Just as temperature emerges from the collective motion of atoms, spacetime could arise from the entanglement of quantum bits or qubits. When two particles become entangled, their properties correlate instantly, no matter how far apart they are. string enough of these connections together, and you don't just get quantum weirdness, you get geometry. Researchers like Brian Swingle and Mark van Romsdonk have shown that under the right conditions, entanglement can literally warp space, creating the illusion of distance where there's only data. Now, here's where it gets tangible. In labs around the world, scientists are testing this theory using quantum computers as cosmic simulators. By programming qubits to mimic the behavior of entangled particles, they've watched as simple spacetime geometries like curved landscapes or even tiny wormholes emerge from pure information. One groundbreaking experiment at Google's Quantum AI lab recreated a holographic wormhole, not with exotic matter or black holes, but with 9 qubits entangled in just the right way. The result, a bridge between 2 points in the simulation built entirely from quantum links. But the real shocker is what this implies about black holes. If spacetime emerges from entanglement, then falling into a black hole might not mean vanishing into a singularity. Instead, your information could remain smeared across its event horizon, entangled with the Hawking radiation leaking out. It's as if the universe has a failsafe. Even when space and time break down, the underlying quantum connections endure. Critics, of course, point out the gaps. Simulating a toy model on a quantum computer isn't the same as proving our universe works this way. Yet the theory's power lies in its ability to solve paradoxes like how black holes can both destroy information and obey quantum mechanics with a single stroke. If spacetime is emergent, then gravity isn't a force but a side effect, a shadow cast by quantum entanglement's invisible hand. So the next time you glance at the night sky, consider this. The vast expanse between stars might not be empty space, but a tapestry of quantum threads vibrating with every particle's whisper. And if we're right, unraveling those threads could reveal reality's truest nature, not as a stage but as a story written in the language of entanglement. What if the tiniest building blocks of matter weren't particles at all but black holes? That's the jaw-dropping premise of the black hole electron theory, where electrons aren't point-like dots but microscopic singularities, each spinning at the edge of reality. Picture this, an electron as a black hole so small, its event horizon would be 1 billion times tinier than an atom. Yet according to the math of Kerr-Newman black holes, solutions to Einstein's equations that describe spinning, charged singularities, this isn't just fantasy. The numbers align eerily well. An electron's charge, mass, and even its quantum spin match the properties of a Kerr-Newman black hole with Planck scale dimensions. It's as if nature left a clue, hiding a gravitational monster inside the humblest particle. But how could this possibly work? Quantum mechanics treats electrons as fuzzy clouds of probability, while black holes are gravitational prisons where spacetime itself tears apart. The trick lies in scale. At distances far larger than the Planck length, the black hole's intense gravity would mimic the electromagnetic force, creating the illusion of a charged particle. Spin, that intrinsic quantum property making electrons behave like tiny tops, wouldn't come from literal rotation, but from the black hole's frame dragging effect, warping spacetime around it like a cosmic whirlpool. Even stranger, the Heisenberg uncertainty principle might emerge naturally. A microscopic black hole's position would constantly fluctuate due to quantum foam, making precise measurement impossible, exactly what quantum mechanics predicts. The implications are staggering. If electrons are black holes, then every atom in your body contains billions of them, a fractal zoo of singularities, each humming with compressed spacetime. This could bridge general relativity and quantum mechanics, two theories famously at odds, by showing gravity's fingerprints on the smallest scales. No more spooky action at a distance, just warped geometry dictating quantum behavior. Even antimatter gets an elegant explanation. Positrons might be these same black holes spinning backward in time, a twist straight out of relativity's playbook. Yet the theory isn't without fatal flaws. For one, black holes decay via Hawking radiation, evaporating over time. an electron-sized black hole would vanish in nanoseconds, yet electrons appear stable. Some theorists propose extra dimensions or exotic physics to stabilize them, but these fixes feel speculative. Worse, the information paradox rears its head. If electrons are black holes, what happens to the data of particles they swallow? Quantum mechanics forbids information loss, but black holes seem to obliterate it. The math also struggles to explain why all electrons are identical, a hallmark of quantum fields, when black holes in nature vary wildly. Still, the idea lingers, a tantalizing what if at the edge of physics. Maybe electrons aren't black holes, but what if they're shadows of them, projections from some deeper layer of reality? After all, black holes and electrons both defy classical intuition, both warp spacetime in their own ways, both guard secrets at their cores. Whether the theory holds or collapses, it forces us to confront a humbling truth. The closer we look at the familiar, the stranger it becomes. The electron, that workhorse of chemistry and technology, might be the universe's greatest sleight of hand, a black hole in disguise hiding in plain sight. Time crystals sound like something ripped from a sci-fi novel, structures that repeat not in space, but in time, ticking like quantum metronomes without ever winding down. Unlike ordinary crystals where atoms arrange in predictable spatial patterns, time crystals defy one of physics' most sacred principles, the symmetry of time. Normally, the laws of physics don't care if you run the clock forward or backward, but time crystals break this rule, creating a system that oscillates perpetually without energy input, like a clock that ticks forever without batteries. The wild part, they're real. In 2017, researchers at the University of Maryland and Harvard took chains of charged atoms, ions, and zapped them with laser pulses to nudge them into this bizarre state. Instead of settling into equilibrium like normal matter, the ions kept flipping their spin directions rhythmically, locked in a loop that couldn't be explained by classical physics. It wasn't perpetual motion in the old pseudoscience sense. No energy was being extracted. Instead, the system found a loophole in quantum mechanics, exploiting entanglement to sustain its beat indefinitely. But why does this matter beyond lab curiosities? For one, time crystals might hold clues to one of cosmology's biggest mysteries, dark matter. Some theories suggest dark matter could be composed of exotic quantum states that don't interact with light but still influence gravity. If dark matter particles behave like time crystals existing in persistent, repeating configurations, it could explain why they're so elusive. They're not just hiding, they're operating on a rhythm entirely outside our usual perception of time. Even more tantalizing, time crystals could revolutionize quantum computing. Their stable, fault-tolerant oscillations might serve as perfect quantum memory cells, preserving information against the decoherence that plagues other systems. Imagine a quantum hard drive that never degrades, its data encoded in the unbreakable rhythm of a time crystal's dance. Yet the most mind-bending implication lies in what time crystals say about the nature of time itself. If matter can lock into a pattern that resists entropy's pull, it hints that time might not be the uniform river we think it is. Instead, it could have texture, structures, and eddies where the arrow of time bends or even folds back on itself. Time crystals don't just challenge our understanding of matter, they whisper that time, too, might be a thing we can engineer. So the next time you glance at a clock, consider this. Somewhere in a lab, a tiny piece of the universe is ticking to a rhythm all its own, oblivious to entropy's march, a shimmering hint that reality's rules are far stranger than we dreamed. Here's a paradox so bizarre it might keep cosmologists awake at night. What if you're not the product of 14 billion years of cosmic evolution, but just a fleeting flicker in the quantum void? Meet the Boltzmann brain, a thought experiment so unsettling it suggests self-aware entities could spontaneously arise from random quantum fluctuations far more easily than entire universes capable of birthing life. The idea traces back to Ludwig Boltzmann, the 19th century physicist who linked entropy to probability. if the universe tends toward disorder over time, rare decreases in entropy statistical flukes should occasionally create order from chaos. Most times that means a brief swirl in a gas cloud, but given enough time, it could mean a fully formed brain, complete with false memories of a past that never existed, hallucinating an entire reality into being. Now crank that up to quantum levels. In an eternal universe or a bubbling multiverse, random fluctuations in quantum fields might conjure conscious observers directly, without the messy intermediate steps like galaxies, planets, or biology. These quantum Boltzmann brains wouldn't need star nurseries or Darwinian selection, just the right improbable alignment of particles to spark awareness. And here's the terrifying part. Statistically, these freak observers should vastly outnumber evolved ones like us. After all, it's infinitely more probable for a single self-aware mind to pop into existence by accident than for an entire life-supporting cosmos to assemble itself. This isn't just philosophical wordplay, it's a direct challenge to cosmology's foundations. If the universe is eternal or cyclic, Boltzmann brains should dominate reality, rendering our existence absurdly improbable. The fact that we don't see the universe teeming with these disembodied minds suggests something's profoundly wrong with our models. Maybe the cosmos isn't eternal after all. Perhaps it had a definite beginning, like the Big Bang, cutting off the infinite time needed for Boltzmann brains to arise. Or maybe undiscovered physics actively prevents such aberrations, a cosmic failsafe ensuring only legitimate observers evolve. Some theorists even invoke the Holographic Principle. We don't encounter Boltzmann brains because their hallucinations wouldn't form stable, shared realities like ours. Yet the problem lingers like a ghost in the equations. If quantum fluctuations can generate virtual particles from nothing, why not virtual minds? Every second, the quantum foam births countless particles fleetingly into existence. Given enough tries, might one briefly achieve consciousness? The implications would rewrite not just cosmology but epistemology. How could you trust any memory or observation if your very brain might be a transient glitch? Perhaps the only escape is to accept that something, dark energy, quantum gravity, or a deeper layer of reality steers the universe away from such chaos. Or maybe, just maybe, the Boltzmann brain paradox is the universe's way of telling us we're missing a fundamental piece of the puzzle. Either way, it's a humbling reminder that in the quantum wilderness, even existence itself might be up for grabs. The notion that entangled particles might be invisibly stitched together by spacetime itself sounds like pure fiction, until you realize Einstein himself hinted at it decades ago. Enter ER equals EPR, a theory so audacious it rewrites quantum weirdness as geometry. Proposed by Juan Maldeisner and Leonard Susskind, this idea dares to suggest that when particles become entangled, they aren't just mysteriously linked. They're literally tethered by microscopic wormholes threading through the fabric of reality like cosmic subway tunnels. Think of it like this: when you toss two coins and they somehow always land matching, quantum mechanics calls it entanglement, but general relativity scoffs nothing influences anything faster than light. ER equals EPR offers a breathtaking compromise. The ER refers to Einstein-Rosen bridges, better known as wormholes, while EPR nods to Einstein, Podolsky, and Rosen's famous paradox about entanglement. The theory merges them into a single revelation. What if the spooky action at a distance isn't action at all, but structure? The wormhole doesn't transmit information. It is the connection, a shortcut through spacetime's folds, making the particles neighbors despite cosmic separations. This isn't just poetic metaphor. The math shows that the geometry of certain wormhole solutions in general relativity perfectly mirrors the quantum correlations of entangled particles. It's as if spacetime itself pirouettes to preserve Einstein's speed limit, bending so entangled particles never actually communicate. They're just closer than they appear. Even black holes fit the puzzle. When two black holes entangle, their interiors might secretly merge via wormholes, creating a bridge where none was visible from outside. But how could such wormholes exist without collapsing instantly? Quantum mechanics offers a lifeline: negative energy. In the bizarre world of quantum fields, the vacuum isn't empty. It's a seething froth where particle pairs blink in and out of existence. Sometimes these virtual particles borrow energy from the future, creating fleeting pockets of negative energy, exotic stuff that could, in theory, prop a wormhole open just long enough to sustain entanglement's embrace. The implications are staggering. If ER equals EPR holds, then every entangled pair in the universe, from lab photons to particles in distant galaxies, might be nodes in a sprawling network of Planck-scale wormholes. Quantum non-locality wouldn't violate relativity. It would embody it, showcasing spacetime's hidden flexibility. Even teleportation gets a cosmic upgrade. Transmitting quantum information through a wormhole could literally mean sending it through spacetime's backdoor. Of course, skeptics pounce. No one's ever observed a wormhole, let alone a microscopic one. The theory also skirts the edge of testability. How do you detect a structure potentially quintillions of times smaller than an atom? Yet tantalizing hints emerge. Some physicists speculate that if we could precisely measure the quantum noise of empty space, we might find anomalies hinting at these wormholes' presence. Others suggest that simulating wormhole dynamics on quantum computers, as Google's team tentatively did in 2022, could offer indirect proof. Whether ER equals EPR survives or collapses, it forces us to confront a radical truth. The universe might not choose between quantum mechanics and relativity. Instead, it could be playing a deeper game where the threads of entanglement aren't just connections, but the very warp and weft of spacetime's hidden architecture. And if that's true, then every time particles entangle, they're not breaking the rules, they're revealing the board on which the game is really played. Paul Dirac once proposed something so outrageous that even his fellow physicists laughed: a cosmic ocean, invisible and infinite, where every drop was an electron. This was the Dirac Sea, a revolutionary idea that predicted antimatter before anyone had seen it. Picture the vacuum not as empty space, but as a churning quantum foam, packed wall to wall with electrons occupying every possible energy state. Normally, we'd never notice this sea. It's perfectly uniform, like a pitch-black room where you can't tell if your eyes are open or closed. But when an electron gets kicked out, it leaves behind a hole, an absence that behaves exactly like a particle with opposite charge, antimatter. At the time, critics dismissed it as mathematical fantasy. Why invent an unobservable ocean just to explain a few equations? But Dirac's stubbornness paid off. When Carl Anderson discovered the positron in 1932, a perfect match for Dirac's holes, the laughter turned to awe. Overnight, the Dirac Sea transformed from heresy to prophecy, proving that even the wildest ideas could hide kernels of truth. Fast forward to today, and quantum field theory has refined Dirac's vision. The vacuum isn't a static sea but a roiling quantum field, where particle-antiparticle pairs constantly blink in and out of existence. These virtual particles aren't just mathematical tricks. They have real effects like the Casimir force, where two metal plates in a vacuum inexplicably attract each other because the space between them suppresses certain quantum fluctuations. Even black holes leak Hawking radiation, particle pairs born from the vacuum where one falls in and the other escapes, yet the spirit of the Dirac Sea endures. Modern theories like the Higgs mechanism borrow its logic, treating the vacuum as an active participant in physics rather than passive backdrop. The Higgs field, for instance, isn't empty. It's a syrup-like medium that gives particles mass as they slog through it, echoing Dirac's intuition that nothingness might be the most interesting thing of all. So was Dirac wrong? Not exactly. His sea was a crude map of a territory we're still exploring, a first draft of quantum field theory's richer picture. And in science, that's how progress works. Sometimes you need a flawed but bold idea to light the way. The Dirac Sea reminds us that reality's strangest truths often lurk where others see only absurdity, waiting for the right mind to dive in and prove them real. What if the universe has a built-in failsafe to keep quantum weirdness from leaking into our everyday world? That's the promise of objective collapse theories, which argue that wave functions don't need conscious observers to collapse. They crumble on their own, as if reality has a quantum expiration date. The most famous of these, the Garadi-Rimini-Weber or GRW theory, proposes that particles spontaneously localize at random intervals, snapping from fuzzy probability clouds into definite positions. It's like a cosmic game of musical chairs where the music stops unpredictably, forcing particles to choose a seat. Here's how the math plays out. For a single electron, GRW predicts a collapse roughly once every 100 million years, rare enough to preserve quantum effects in atoms. But scale up to macroscopic objects and the odds shift dramatically. A human-sized mass contains around 10 to the 27th power particles, so statistically, some part of you should experience spontaneous collapse every billionth of a second. These micro-collapses add up, effectively freezing large objects in classical states while leaving microscopic ones free to quantum dance. It's a clever fix for Schrödinger's cat. The feline never exists in superposition because its trillions of particles are constantly being nudged toward definiteness by nature itself. Yet there's a rival in the Ring-Diossi-Penrose or DP theory, which swaps randomness for gravity. Roger Penrose argued that spacetime can't tolerate the energy disparities created by quantum superpositions. When the strain becomes too great, spacetime protests by collapsing the wave function. Picture a stretched rubber sheet. Eventually, it must snap back to equilibrium. In this view, your coffee cup stays on the table not because you look at it, but because the gravitational cost of it existing in two places at once is too high for the universe to sustain. The kicker: these theories make testable predictions. GRW suggests collapse leaves subtle traces, a faint background noise of energy depositions that could be spotted in ultra-sensitive experiments. DP goes further, predicting that collapse events emit minuscule bursts of radiation as spacetime recoils. No one's definitively caught these signals yet, but labs are hunting. The Nobel-winning discovery of neutrino mass used similar ultra-pure detectors, hinting we might have the tech to find collapse's fingerprints. Objective collapse doesn't just tidy up quantum mysteries, it reshapes how we view reality's scaffolding. If true, the boundary between quantum and classical isn't about size or complexity, but a cosmic balancing act between randomness and gravity, noise and structure. And somewhere in that tension lies a truth far stranger. The universe might not need us to observe it at all. It could be observing itself. What if the probabilities in quantum mechanics aren't facts about the world, just your personal bets? That's the provocative heart of quantum Bayesianism or cubism, a theory that flips quantum weirdness on its head by treating probabilities not as objective features of reality, but as subjective degrees of belief. Imagine flipping a coin before it lands. Quantum mechanics says it's both heads and tails until observed. Cubism goes further. It claims the both isn't out there in the universe. It's inside you, a reflection of your own uncertainty. The coin was always one or the other, you just didn't know yet. This perspective cracks open the infamous Wigner's friend paradox, a thought experiment where a physicist, let's call him Eugene, observes a quantum system inside a lab while his colleague Wigner stands outside. To Eugene, the system's wave function collapses the moment he looks, but to Wigner, who hasn't peaked yet, Eugene and the system remain entangled in superposition. So who's right? Traditional quantum mechanics stumbles here. Trapped in infinite regress, does reality solidify only when a conscious observer intervenes? And who counts as one? Cubism cuts the knot. There's no paradox because there's no single objective reality to argue about. Eugene's observations update his beliefs, Wigner's update his. The probabilities aren't describing some mystical quantum fog. They're just personal scorecards tracking each observer's individual bets. Think of it like weather forecasts. When a meteorologist says there's a 70% chance of rain, they're not claiming the atmosphere is in a superposition of raining and not raining. They're expressing confidence based on imperfect data. Cubism treats quantum probabilities the same way. An electron's spin isn't physically both up and down. It's just that your knowledge is incomplete, so you assign odds. The act of measuring isn't magically collapsing reality. It's you finally getting the answer to your question. But Cubism's real power lies in how it sidesteps quantum theory's thorniest puzzles. Take Schrödinger's cat. Instead of wrestling with a zombie cat that's simultaneously dead and alive, a cubist shrugs. The cat was always one or the other. The probabilities just reflected your ignorance. Even entanglement gets demystified. Those spooky correlations between particles, just two agents comparing notes and realizing their beliefs sync up in unexpected ways. Critics, of course, recoil at Cubism's radical subjectivity. If quantum mechanics is all about personal belief, does that mean reality itself splinters into billions of observer-dependent fragments? Cubists counter that the world exists just independently of our probabilistic descriptions of it. The moon isn't there because you look, it's there, and you're assigning numbers to what you think you'll see. It's a subtle distinction, but a crucial one. Cubism doesn't deny reality. It just insists that quantum mechanics isn't its blueprint, it's our user manual. So why does this matter beyond philosophy? Because Cubism reframes quantum theory as a tool for decision-making, not a window into ultimate reality. It's why your quantum computer can solve problems without the universe caring whether its qubits are truly in superposition. The probabilities work either way, and in a world where quantum tech is booming from encryption to AI, that pragmatic shift might be the key to unlocking its full potential. After all, if quantum mechanics is just a language for betting wisely, then the house always wins as long as you play the odds right. Imagine standing at a crossroads where every possible path doesn't just exist in theory, it splits into a new universe, each one playing out a different version of reality. This is the spine-tingling heart of the multiverse interpretation, where Hugh Everett's radical vision redefines quantum mechanics not as a game of chance, but as a cosmic branching machine. Every quantum decision, every flicker of uncertainty spawns a new timeline, meaning there's a universe where you took that job offer, one where dinosaurs never went extinct, even one where Elvis is still flipping pancakes in a diner in Memphis. But here's the kicker, these branches aren't science fiction. They're the direct consequence of quantum fields evolving under Schrödinger's equation, never collapsing, just endlessly dividing like a fractal tree of existence. The math behind this is deceptively simple. When a particle's wave function encounters a choice, say, passing through one slit or another in the double-slit experiment, Everett argued it doesn't pick. Instead, the universe multiplies. One version sees the particle go left, another sees it go right. Neither outcome cancels the other. Both unfold in parallel, their histories forever diverging. Scale this up to human decisions and the numbers explode. Right now, as you watch this, your neurons are firing in quantum superpositions, every micro-choice blinking, breathing, doubting, triggering new branches. Statisticians estimate that within the last minute alone, the number of yous splintered into parallel worlds could exceed the atoms in the observable universe. But is this physics or philosophy? Critics pounce on the theory's biggest hurdle. If these branches are real, why can't we detect them? The answer lies in decoherence, the process where quantum systems get tangled with their environment, making alternate timelines effectively invisible to one another. Think of it like radio stations playing simultaneously. Your receiver can only tune into one frequency at a time, even though the others are broadcasting. In this view, the multiverse isn't hiding, we're just locked into a single channel of the cosmic spectrum. Yet the implications rattle our sense of identity. If every quantum flutter spawns a new you, then death itself becomes illusory. In some universe, your consciousness always persists, dodging every bullet, surviving every accident. It's a comforting thought until you realize it also means there are branches where your worst fears came true, where every regret is someone else's reality. The debate rages on. Some physicists argue the multiverse is an untestable cop-out, a way to dodge quantum mechanics' deeper mysteries. Others see it as the only interpretation that fully respects the math, avoiding the ad hoc collapse rule of traditional quantum theory. And then there's the wild card. What if these branches aren't just abstract math but literal worlds bubbling into existence like quantum foam? If so, then reality isn't just bigger than we imagined, it's bigger than we can imagine, a hall of mirrors where every reflection is real and every choice echoes forever. So the next time you hesitate over a decision, remember, somewhere you didn't, and that version of you is just as convinced they're the real one. The multiverse doesn't just rewrite physics, it redefines what it means to exist. Among the countless mysteries of the cosmos, dark matter stands as one of the most perplexing and invisible substance that outweighs visible matter 5-to-1. Yet refuses to interact with light or any known force except gravity. Scientists have hunted for decades, searching for clues in particle colliders and distant galaxies. But what if the answer lies not in some exotic new physics, but in a ghostly quantum field left over from the birth of the universe? Enter actions, hypothetical particles so light they barely exist, yet could collectively form the hidden scaffolding of reality itself. Unlike their flashier dark matter candidates, WIMP or primordial black holes, actions move through the cosmos with glacial patience, their sluggishness earning them the nickname cold dark matter. Imagine a vast, invisible ocean where each droplet is an action, drifting so slowly that a single particle might take minutes just to cross the width of an atom. This cosmic slowness isn't accidental, it's baked into their origins. Theory suggests actions emerged in the earliest moments after the Big Bang, when a quantum field called the Peck-Quinn field froze into place, its ripples condensing into these ultralight particles. Unlike energetic particles zipping at near light speed, actions barely budge, clustering into diffuse halos that envelop galaxies like silent shrouds. But how do you catch something that barely interacts with anything? The trick lies in action's faint but telltale signature. In the presence of strong magnetic fields, they should occasionally convert into microwaves. Picture an invisible snowflake landing on your palm and just for an instant flashing into a spark before vanishing. That's the hope-driving experiments like ADMX and Haystack, where scientists use superconducting cavities chilled near absolute zero to amplify these rare conversions into detectable signals. It's like tuning a cosmic radio to a frequency no natural source should broadcast, listening for whispers from the quantum void. The stakes couldn't be higher. If actions are real, they'd solve two cosmic riddles at once: the nature of dark matter and the strong CP problem, a head-scratcher in particle physics about why certain quantum interactions violate symmetry less than expected. Actions elegantly balance these equations, acting as nature's reset button to restore symmetry to the early universe. Some theories even suggest actions could form Bose-Einstein condensates, quantum superstructures spanning light years, their collective behavior warping spacetime in ways we've yet to imagine. Yet the hunt is fiendishly difficult. Actions could be billions of times lighter than electrons, requiring detectors sensitive enough to spot a needle in a galactic haystack. Recent breakthroughs like quantum squeezing techniques that reduce measurement noise are pushing the limits of what's possible. And if we succeed, the payoff would be staggering, not just proof of actions, but a window into the quantum fields that shape the cosmos. These whispers from the dawn of time might finally reveal why the universe looks the way it does and what invisible hands are still pulling its strings. Until then, the search continues, a high-tech treasure hunt for the universe's shyest particles. What if the very act of accelerating through empty space could conjure heat and particles out of nothing? This is the Unruh effect, a quantum phenomenon so counterintuitive it blurs the line between observation and reality. Picture an astronaut floating in the vacuum of space, no stars, no planets, just pure blackness. To them, the universe appears cold and empty, barely above absolute zero. But now imagine they fire their thrusters, accelerating faster and faster. Suddenly, their instruments detect something impossible, a warm glow. Not from stars or cosmic dust, but from space itself. The vacuum, silent and still to an outside observer, now shimmers with particles, as if their acceleration has torn open a hidden layer of reality. The math behind this revelation is staggering. Quantum fields, which underlie all particles, aren't static, they vibrate with energy even in so-called empty space. To an accelerating observer, these vibrations don't just hum, they roar. The faster you accelerate, the more the quantum field's oscillations appear distorted, like a cosmic Doppler effect. What was once a quiet quantum hum stretches into a chorus of detectable particles, all spawned by motion alone. The temperature of this phantom heat bath depends on acceleration. A human accelerating at a comfortable 1 g Earth's gravity would see space heated to a barely perceptible whisper above absolute zero. But near a black hole's event horizon, where gravity produces extreme acceleration, this effect explodes into significance. Here's where the Unruh effect tangles with one of cosmology's great puzzles, Hawking radiation. Just as acceleration makes particles appear from the vacuum, so does gravity's grip near a black hole. An observer falling in sees nothing unusual at the event horizon, but someone hovering outside would detect a glow of radiation, Hawking's famous prediction. The Unruh effect suggests these phenomena are two sides of the same coin. Both arise from how observers in different states of motion perceive quantum fields. To the hovering observer, the black hole's gravity acts like relentless acceleration, heating the vacuum just as a rocket's thrust would. This raises a mind-bending question. Is reality truly observer-dependent at its core? If particles can be real to one observer and absent to another, does that mean existence itself is a matter of perspective? Some physicists argue yes, quantum fields are the only true reality, and particles are just how we perceive their vibrations based on our motion. Others push back, insisting there must be an objective reality beneath the appearances, even if we can't yet describe it. Experimental proof remains elusive. Detecting Unruh radiation directly would require accelerations trillions of times stronger than anything achievable in labs, though clever workarounds, like simulating the effect in supercooled quantum systems, offer tantalizing hints. Meanwhile, the debate rages on. Is the universe a fixed stage, or does it rewrite its script for every observer? The Unruh effect doesn't just challenge our notions of particles and emptiness. It forces us to confront whether reality itself is a shared hallucination, shaped by the motion of those who dare to look. Deep within the quantum realm, where particles dance to rules that defy common sense, there exists a bizarre class of objects that aren't quite particles or waves, but something stranger, anyons. These exotic entities only emerge in two dimensions, sliding between one another like spectral braids, their identities shifting with each encounter. What makes them possible? The answer lies in topological quantum field theory, or TQFT, a framework where the universe's most stable phenomena might be encoded not in particles but in knots. Picture space not as a blank stage, but as a tangled tapestry of quantum fields where threads of energy twist and loop into intricate patterns. These aren't just abstract shapes, they're the scaffolding of reality itself. In certain two-dimensional systems, like the thin layers of material used to study the fractional quantum Hall effect, electrons don't just repel each other, they become trapped in a collective dance, forming quasi-particles with fractions of an electron's charge. These are anyons, and their behavior is governed by topology, the mathematical study of shapes preserved under stretching or twisting. Here's where it gets surreal. When two anyons orbit one another, their quantum states don't just change, they remember the path taken, as if the universe keeps a ledger of their movements. This memory is called braiding statistics, and it's nothing like the behavior of familiar particles. Swap two electrons and their quantum wave function stays the same. Swap two anyons and it might pick up a phase shift, a twist in the quantum ledger that depends entirely on how they loop around each other. It's as if the act of braiding leaves an indelible mark on reality, a signature etched into the fabric of spacetime. The implications for quantum computing are staggering. Ordinary qubits are fragile, their delicate superpositions crumbling at the slightest disturbance. But topological qubits built from anyons would be inherently robust, their information encoded not in fleeting quantum states, but in the knots themselves. Untangle the braid wrongly, and the computation fails, but the topology naturally resists errors, like a puzzle that only fits together one way. Microsoft's Station Q Lab has bet big on this idea, pouring resources into engineering materials that could host these elusive quasi-particles. Their goal, a quantum computer where stability isn't fought for, but baked into the physics of the system. Yet TQFT isn't just a playground for futuristic tech, it's a window into the universe's deepest layers. Some theorists speculate that spacetime itself might arise from a more fundamental topological structure, a network of quantum entanglements that only appears smooth from a distance. Others see hints of how gravity could emerge from quantum mechanics, woven into existence by the same braiding rules that govern anyons. Whether these ideas hold or not, one thing's certain. In the quantum world, the most enduring truths might not be written in particles or forces, but in the silent, unbreakable knots they tie. Stephen Hawking's bombshell announcement in 1976 sent shockwaves through physics. Black holes, those cosmic vacuum cleaners, don't just swallow matter, they erase information from existence. According to quantum mechanics, information is sacred. The state of every particle, every interaction, must be preserved forever, like a cosmic ledger that never loses a single entry. Yet Hawking's calculations suggested black holes violate this with terrifying elegance. As they slowly evaporate through Hawking radiation, the particles they emit are random, carrying no trace of what fell in. Poof, history itself vanishes. This wasn't just a puzzle, it was a paradox threatening to unravel the foundations of physics. Enter string theory, wielding its most dazzling weapon, holography. If the AD/CFT correspondence holds, then information isn't lost inside the black hole. It's smeared across its event horizon like quantum graffiti. Every atom, every photon that crosses the point of no return leaves a two-dimensional imprint, scrambled but preserved. Think of it like burning a book. The pages are ashes, but if you had perfect knowledge of how fire transforms ink and paper, you could theoretically reconstruct every word. Black holes might operate the same way, their event horizons acting as quantum error-correcting codes, hiding information in plain sight through entropy's chaos. But just as physicists were catching their breath, a new twist emerged: firewalls. In 2012, a team led by Joe Polchinski argued that if information really escapes a black hole, the event horizon can't be the serene boundary Einstein predicted. Instead, it must be a seething wall of high-energy particles, incinerating anything that approaches. Picture falling toward a black hole expecting empty space, only to hit a cosmic shredder moments before crossing. The firewall paradox forced physicists to choose. Either information preservation is an illusion, or our understanding of spacetime is catastrophically incomplete. The debate rages hotter than a singularity. Some theorists propose black holes are fuzzball strings tangled into dense knots with no sharp horizon. Others suggest information leaks out via quantum wormholes, stitching the interior to Hawking radiation through spacetime's hidden threads. Meanwhile, experiments with quantum computers simulate microscopic black holes, searching for clues in their evaporation patterns. Where does this leave us? Hawking himself reversed course before his death, conceding information might escape after all, etched into the Hawking radiation itself, like a message in a bottle tossed from a sinking ship. The paradox isn't solved, but it stretched our vision of reality further than ever. Whether black holes are cosmic shredders or quantum archivists, one thing's certain: they're not just monsters in the dark. They're the universe's most provocative teachers, forcing us to rewrite the rules of existence itself. Imagine a black hole not in the depths of space, but right here on Earth, trapped in a vat of superfluid helium so cold it defies all friction. This isn't science fiction. It's the cutting edge of quantum gravity research, where physicists use everyday materials to recreate the universe's most extreme phenomena. Take superfluid helium, a liquid that flows without viscosity, climbing walls and forming quantum vortices that spin forever without slowing down. When researchers send ultrasonic waves through this exotic fluid, something remarkable happens. The sound waves get trapped, unable to escape certain regions, just like light near a black hole's event horizon. These sonic black holes don't warp spacetime with gravity. Instead, they use the fluid's flow to mimic the same physics, creating a lab-scale version of Hawking radiation where sound waves split into pairs, one escaping while the other plunges inward. Graphene, that miracle material just one atom thick, offers another playground for spacetime analogies. When electrons zip across its hexagonal lattice at relativistic speeds, they behave as if they're navigating a curved universe. By straining the graphene sheet, stretching or bending it like cosmic origami, scientists can engineer artificial gravitational fields. Electrons speeding through these warped regions act like stars orbiting a black hole, their paths twisting in ways that eerily resemble Einstein's predictions. It's as if the cosmos left a backdoor in quantum physics, letting us test general relativity on a desktop. But why stop at simulation? These analog systems might hold clues to the real thing. In 2014, a team at the Technion in Israel observed spontaneous sound waves in a Bose-Einstein condensate, a state of matter chilled to near absolute zero, that matched predictions for quantum fluctuations near a black hole. No telescope required, the evidence was there, vibrating in a cloud of ultra-cold atoms. Meanwhile, in graphene, researchers have spotted electronic versions of wormholes where electrons seem to tunnel through impossible barriers, as if spacetime itself had a shortcut. The implications are staggering. If quantum gravity leaves fingerprints in condensed matter, then the universe might be far more modular than we thought, a place where the same mathematical rules govern black holes and superconductors alike. And as we refine these experiments, inching closer to detecting Hawking radiation in a droplet of helium or mapping spacetime's birth in a graphene chip, we're not just mimicking the cosmos. We're reverse engineering its deepest secrets, one quantum analogy at a time. The universe has a secret, one so baffling it makes black holes look simple. It's called the cosmological constant problem, and it's the starkest mismatch between prediction and reality in all of science. Quantum field theory calculates that empty space should fizz with unimaginable energy, a seething quantum foam so dense it ought to curve the universe into a singularity within moments of the Big Bang. And yet, when we measure the actual energy of the vacuum, it's almost zero, a whisper so faint it barely nudges cosmic expansion. The discrepancy isn't a minor rounding error. It's a factor of 10 to the power of 120, a number so vast it defeats analogy. If the predicted vacuum energy were the volume of the observable universe, the measured value would be a single atom. So where did the math go wrong? One possibility is that we're missing something fundamental about quantum fields. maybe gravity doesn't respond to vacuum energy the way we think, our idea called degravitation, where the universe effectively filters out extreme energy densities. Picture a sponge absorbing water until it's saturated. Beyond a certain point, adding more doesn't increase the weight. If spacetime operates similarly, it could explain why the vacuum's fury doesn't rip reality apart. Some theories even suggest gravity might weaken at cosmic scales, diluting the effects of vacuum energy like a sieve straining out the universe's excess. Yet there's another, more contentious solution, the anthropic multiverse. If infinite universes exist with randomly varying constants, we'd inevitably find ourselves in one where the cosmological constant is improbably small, because anything larger would make galaxies, stars, and life impossible. It's a cosmic version of the lottery. The odds of winning are minuscule, but someone has to win. Critics recoil at this logic, calling it a surrender to coincidence. But supporters argue it's no different from acknowledging Earth's Goldilocks position in the solar system, a rare but necessary condition for our existence. The stakes couldn't be higher. If the multiverse explains the cosmological constant, it implies nature's laws aren't fine-tuned but post-selected, with life emerging only in the rare pockets where numbers align. Conversely, if degravitation or another untested physics holds the answer, we might be on the verge of rewriting how gravity and quantum fields intertwine. Either way, the solution or the absence of one will redefine our place in the cosmos. The vacuum's silence isn't just a puzzle, it's a screaming clue that reality is stranger than our equations can yet grasp. Ever wondered why the quantum world feels so alien compared to our everyday reality? Why atoms can exist in multiple states at once while cats or coffee cups seem stubbornly definite? That's the puzzle quantum Darwinism aims to solve. Picture Schrödinger's infamous cat, neither dead nor alive, trapped in its box of quantum uncertainty. According to Wojciech's groundbreaking theory, the cat doesn't need a human observer to collapse its fate. Instead, it's constantly bombarded by photons, air molecules, even cosmic rays, each interaction acting like a tiny vote in nature's ballot box. Over time, one outcome gains overwhelming support while the other fades into obscurity, not because of consciousness, but because the environment itself serves as a relentless editor, amplifying the most stable state. Think of it like a quantum game of telephone. A particle starts in superposition, say, spinning both clockwise and counterclockwise, but every collision with its surroundings leaks information. Photons scatter off it, air molecules bump into it, and each interaction leaves a microscopic imprint. These imprints aren't random, they form redundant copies of the particle's state, like whispers passed through a crowd. By the time you open the box, the universe has already tallied the votes. The cat's alive or dead not because you looked, but because the environment has broadcasted one outcome far louder than the other. This isn't magic, it's natural selection operating at the quantum level, where the fittest states survive by proliferating their information. Lab experiments with entangled particles reveal this process in action. When quantum systems interact with their environment, their fragile superpositions unravel through decoherence, leaving behind only the most robust classical states. It's as if reality has a built-in filter, sifting through quantum possibilities and discarding the unstable ones. Quantum Darwinism takes this further, suggesting the states we perceive as real are simply the ones best at replicating themselves. A chair isn't in a definite position because some cosmic observer wills it. It's because its location has been copied countless times by photons bouncing off it, air molecules nudging it, dust settling on its surface. The universe isn't passively observed, it's actively broadcasting classical reality through a chorus of environmental interactions. The implications ripple far beyond Schrödinger's cat. If quantum Darwinism holds, free will gets a subtle twist. Our choices might emerge not from some ethereal soul, but from the quantum states most resilient to decoherence, winnowed by the relentless sieve of the environment. Even time's arrow could be a side effect, an illusion created by the irreversible spread of quantum information into the world and the eerie quantum underpinnings. They're still there, humming beneath the surface, filtered out by the ruthless democracy of the cosmos. So the next time you flip a light switch or catch a ball, remember, the solid, predictable world around you might just be nature's greatest hits album, a collection of quantum states so good at replication they've become the only reality you'll ever know. And the bizarre quantum shadows, they never left, they're just waiting backstage, silenced by the noise of existence itself. What if quantum events aren't governed by chance or observation, but by a conversation between the past and future, a cosmic negotiation where cause and effect blur into a single timeless loop? That's the startling premise of the transactional interpretation, a theory that flips quantum mechanics on its head by introducing retrocausality, the idea that future events can reach backward in time to shape the present. Proposed by physicist John Cramer in the 1980s, this model suggests that particles don't just exist in fuzzy superpositions until measured. Instead, they're caught in a dance of handshakes, where waves of probability travel both forward and backward through time, meeting in the middle to create what we perceive as reality. Picture a photon racing toward a double-slit experiment. In the standard view, it's a wave of possibilities until it hits the detector, collapsing into a particle. But Cramer's interpretation paints a stranger picture. The detector doesn't just receive the photon, it sends a signal backward through time, a kind of quantum RSVP that tells the photon how to behave before it even arrives. This offer wave from the past meets a confirmation wave from the future, and their agreement, their transactional handshake, is what we observe as a definite event. It's as if the universe runs on a system of cosmic pre-orders, where outcomes are settled not in the moment, but across time itself. The most jaw-dropping evidence for this comes from delayed choice experiments, where scientists seem to rewrite quantum history with a simple flick of a switch. In one landmark setup, particles are given a choice: act as waves or particles by passing through one or both slits. But here's the twist. The decision to measure which slit they took is made after the particles have already passed through. Astonishingly, the particles behave as if they know the future measurement, adjusting their past actions accordingly. If you choose to measure the slits, they act like particles. If you don't, they've always been waves. It's as if the future reaches back to edit the script of the past. Critics argue this smacks of time travel paradoxes. How can an effect precede its cause without unraveling reality? Cramer counters that these handshakes aren't true causality violations, just a deeper symmetry hidden in quantum math. The universe, he suggests, isn't a one-way street but a Mobius strip of cause and effect, where the future and past are partners in a timeless negotiation. Some even speculate this could explain entanglement's spooky action. When particles correlate instantly across space, they're not communicating faster than light. They're simply settling a deal brokered across time. The implications ripple far beyond the lab. If the transactional interpretation holds, free will gets a bizarre twist. Our choices might not just shape the future but retroactively sculpt the past. The universe becomes less a clockwork mechanism and more a vast, self-consistent story, where every event is co-authored by what's to come. And while mainstream physics still favors less radical models, Cramer's vision lingers like a ghost in the equations, a reminder that in the quantum realm, time might not flow the way we think. It could be a two-way street, with reality itself the product of countless handshakes across the ages. What if the tiniest building blocks of matter weren't particles at all, but gravitational monsters in disguise? The black hole electron theory proposes exactly that. An electron as a microscopic singularity so small its event horizon would be 1 billion trillion times tinier than an atom. At first glance, the idea seems absurd. How could something as fundamental as an electron harbor a spacetime tear inside? Yet when you examine the numbers, something eerie emerges. The properties of a spinning, charged Kerr-Newman black hole, a solution to Einstein's equations, align uncannily well with an electron's quantum characteristics. Its charge matches perfectly, its mass fits, even the electron's intrinsic spin, that bizarre quantum property making it behave like a tiny top, mirrors the frame-dragging effect of a rotating singularity warping spacetime around it. This isn't just numerical coincidence, it suggests gravity and quantum mechanics might be two faces of the same cosmic coin. Imagine an electron's so-called point-particle nature isn't a feature of quantum fields, but the event horizon of a Planck-scale black hole. From afar, its intense gravitational field would mimic electromagnetic forces through spacetime curvature, creating the illusion of a charged particle. Quantum spin wouldn't come from some abstract internal property, but from literal rotation twisting the fabric of reality at microscopic scales. Even Heisenberg's uncertainty principle finds new footing. The position of such a tiny black hole would constantly fluctuate due to quantum foam, making precise measurement impossible by default. Yet the theory stumbles on brutal paradoxes. For one, Hawking radiation should make these micro-black holes evaporate in nanoseconds, yet electrons appear perfectly stable. Some theorists propose extra dimensions could stabilize them, wrapping the singularities in cosmic duct tape. Another fatal flaw: information preservation. If electrons swallow incoming particles through microscopic event horizons, what happens to quantum information? Standard black holes already threaten to violate quantum mechanics by destroying data. Now scale that problem down to every atom in the universe. Even more damning, all electrons are identical, a hallmark of quantum field theory. While naturally forming black holes vary wildly in mass and spin, perhaps the truth lies somewhere between. Maybe electrons aren't literal black holes, but excitations in a deeper quantum gravitational field that merely resemble them, shadows cast by structures we can't yet perceive. Whether the idea survives or collapses, it forces us to confront how little we truly understand about the familiar. The electron, that humble workhorse powering chemistry, technology, and life itself, might be hiding the universe's greatest sleight of hand. A whisper of gravity's reach into the quantum realm, or perhaps evidence that spacetime itself emerges from something even stranger. The holographic principle doesn't just challenge our perception of reality, it shatters it, suggesting the three-dimensional world we experience is nothing more than a shimmering mirage projected from a flat, two-dimensional surface at the edge of the cosmos. This isn't metaphor or speculation, it's a rigorous mathematical framework born from the study of black holes, where Leonard Susskind and Gerard T. Hooft made a staggering realization. The information swallowed by a black hole doesn't vanish into oblivion. Instead, it gets smeared across the event horizon like cosmic graffiti, perfectly preserved in a scrambled, two-dimensional code. Stretch this idea to its logical extreme, and the entire universe might operate the same way, a hologram where the real action happens on a distant boundary, and everything we see is just a shadow cast by that deeper reality. String theory amplifies this bizarre vision. In the realm of brain's higher dimensional objects posited by string theorists, our universe could be a three-dimensional slice floating in a higher dimensional space, with all its information encoded on a two-dimensional surface like a movie projected onto a screen. The equations reveal something even more startling. The amount of information any region of space can hold isn't infinite. It's capped by the area of its boundary, not its volume, a cosmic version of pixel density. Pack too much data into a space, and the universe literally runs out of storage, blurring the details like an overstretched JPEG. This information limit implies that even empty space isn't truly empty. It's a seething network of fundamental bits, a digital substrate beneath the analog illusion of smooth spacetime. The implications rewrite the rules of existence. If the holographic principle holds, then black holes aren't just cosmic vacuum cleaners, they're Rosetta Stones, revealing how information, space, and quantum fields intertwine. The event horizon becomes a cosmic hard drive, its surface area determining how much data the universe can store. And here's the kicker: this might explain why quantum mechanics and gravity have resisted unification. Gravity isn't a fundamental force, it's an emergent phenomenon, a side effect of information processing on that distant two-dimensional surface, the three-dimensional world we navigate daily. Just a rendering, a high-resolution illusion conjured by the universe's underlying code. Lab experiments are already hunting for hints of this holographic reality. By studying the quantum entanglement of particles near black hole analogs like those created in supercooled Bose-Einstein condensates, scientists hope to spot the telltale signatures of information being encoded on a boundary. Even the fabric of spacetime itself might betray its pixelated nature. If the universe has a resolution limit, then ultra-high-energy cosmic rays could arrive slightly scrambled, their wavelengths distorted by the granularity of space at the Planck scale. Yet the most profound consequence isn't technical, it's philosophical. If we're living in a hologram, then free will, time, and even consciousness might not be what they seem. The universe isn't a clockwork mechanism but a computation, a cosmic simulation running on a two-dimensional substrate. Your thoughts, your memories, the very sensation of being, all might be data points in a vast, unfolding projection. The holographic principle doesn't just demote us from the center of the cosmos, it suggests we're not even three-dimensional beings to begin with. We're shadows on the cave wall, mistaking the flickers for reality. And somewhere on the edge of existence, the universe's true canvas hums with the raw code of everything. Imagine the ground beneath your feet wasn't just solid earth but a thin sheet of ice, frozen over an abyss you never knew existed. That's the precarious reality we might be living in, according to the theory of vacuum decay. Our universe's quantum vacuum, the invisible energy field that permeates all of space, could be in a temporary, metastable state, like a boulder balanced on the edge of a cliff. One quantum nudge and everything we know, every law of physics, every atom in your body, the very fabric of space-time, could vanish in an instant, replaced by a new reality operating under entirely different rules. At the heart of this existential threat lies the Higgs field, the same quantum field that gives particles their mass. In 2012, CERN discovery of the Higgs boson confirmed its existence, but it also revealed something unsettling. Measurements suggest the Higgs field might not be in its true, lowest energy state. Instead, it could be trapped in a false vacuum, like a marble resting in a shallow dent atop a hill. Given enough time or the right trigger, it might roll down into a deeper valley, unleashing a catastrophe unlike anything in cosmic history. Here's how doomsday would unfold. Somewhere in the universe, perhaps in a distant galaxy or even in a high-energy collision at CERN, a tiny bubble of true vacuum forms. This bubble isn't empty space. It's a new phase of reality where the Higgs field has settled into a more stable configuration. Instantly, the laws of physics inside the bubble change. Atoms might no longer hold together. Light could behave differently. Even the fundamental forces might reconfigure. Then the bubble expands, not at the speed of sound or the speed of a rocket, but at the speed of light, rewriting existence as it goes. One moment, stars shine and life thrives. The next, an unstoppable wall of annihilation sweeps through the cosmos, leaving nothing recognizable in its wake. The terrifying part, we'd never see it coming. A bubble expanding at light speed delivers no warning. Its leading edge would reach us at the exact moment we detected it. No time to react, no chance to escape. It's the ultimate cosmic surprise party, except the surprise is the end of physics itself. But why hasn't this happened yet? If the universe is 14 billion years old and vacuum decay is possible, shouldn't we have been obliterated by now? Some theories suggest we're sitting in a cosmic sweet spot, a Goldilocks zone where the Higgs field is just stable enough to last for trillions of years. Others propose undiscovered physics like supersymmetry might shore up the vacuum's fragility. CERN ongoing experiments are crucial here. By probing the Higgs boson's precise properties, scientists can calculate whether our vacuum is truly stable or hovering on the brink. Yet there's a haunting silver lining. If vacuum decay rewrites the laws of physics, the new universe it creates might be more hospitable to life than our own. The constants of nature could align in ways that allow stars to burn longer, chemistry to thrive richer, or even new forms of matter to emerge. In this grim scenario, we'd be collateral damage in the birth of something stranger and perhaps more beautiful, a cosmic phoenix rising from our ashes. So while vacuum decay remains a low-probability nightmare, it forces us to confront a humbling truth. Reality might be far more fragile than it appears. The stage upon which existence plays out isn't set in stone. It's a quantum house of cards waiting for the slightest breeze to collapse. And whether that breeze comes tomorrow or in a googol years, the message is clear: the universe owes us nothing. Its stability is a gift, not a guarantee. Pilot wave theory dares to ask a dangerous question: what if quantum mechanics isn't random at all? While mainstream physics insists particles exist as probability clouds until observed, this radical alternative resurrects an idea from the 1950s. Beneath the quantum frenzy, there's a hidden order guiding every flicker and jump. The brainchild of physicist David Bohm, pilot wave theory proposes that particles aren't ghosts in the machine, they're tiny boats riding invisible waves. Their paths perfectly predetermined by a quantum potential we can't directly detect. Forget dice rolls, reality becomes a cosmic river with currents steering everything from electrons to galaxies. The beauty of this vision comes alive in a deceptively simple experiment. Imagine a droplet of oil bouncing on a vibrating liquid surface, a setup pioneered by French physicist Yves Cauder. As the droplet hops, it generates waves that in turn guide its future path. The result, the droplet exhibits eerily quantum-like behavior. It tunnels through barriers, recreates interference patterns, even orbits in quantized steps, all without any probabilities or collapses. It's as if the droplet is a macroscopic electron, with its pilot wave playing the role of Bohm's hidden variable. These experiments don't prove pilot wave theory correct, but they offer something equally valuable, a tangible metaphor for how determinism might lurk beneath quantum chaos. Yet for all its elegance, pilot wave theory remains a fringe idea, dismissed by many as a philosophical relic. The resistance isn't just about math, it's about worldview. Mainstream quantum mechanics embraces randomness as fundamental, a feature woven into reality's fabric. By contrast, Bohm's deterministic universe feels like a throwback to classical physics, where every effect has a clear cause. Critics also bristle at the theory's non-locality, where particles instantaneously influence each other across vast distances. Einstein famously called this spooky action at a distance, and pilot wave theory doubles down on it, demanding a cosmic choreography that violates relativity's speed limit. But here's the twist: modern quantum experiments have already shown non-locality is real via violations of Bell's theorem. The real issue isn't whether spooky action exists, but whether we're willing to trade fuzzy probabilities for hidden mechanisms. For many physicists, the math of pilot waves feels clunky compared to the sleek formalism of quantum field theory. Adding unseen variables to explain quantum behavior smacks of adding epicycles to planetary orbits, a complication where elegance should reign. Still, the theory refuses to die. Recent work in quantum foundations has unearthed surprising connections between pilot waves and emergent gravity, hinting that Bohm's hidden variables might someday bridge quantum mechanics and general relativity. Meanwhile, those bouncing droplets continue to mesmerize, proving that determinism can mimic quantum weirdness with startling fidelity. Whether history vindicates pilot wave theory or buries it, its greatest gift might be the questions it forces us to confront. Is the universe really a game of chance, or are we just missing the deeper rules? And if hidden order exists, what else might be lurking beneath the quantum veil? The droplets keep dancing, the waves keep guiding, and the debate rages on, not just about how the universe works, but how deeply we're willing to look before calling something random. So where does this quantum rabbit hole leave us? After journeying through 30 mind-bending theories, from the holographic principle's cosmic projection to vacuum decay's apocalyptic fragility, from the simulation argument's digital mirage to the multiverse's infinite branching, one truth becomes undeniable: reality is far stranger than our textbooks dare to admit. Quantum fields aren't just the universe's hidden scaffolding. They're its greatest magic trick, conjuring particles from emptiness, weaving spacetime from entanglement, and perhaps even encoding existence itself on a distant two-dimensional boundary. Consider the holographic principle, which shrinks our three-dimensional world into a cosmic flat screen, or vacuum decay's chilling reminder that physics itself might be a house of cards. Ponder the simulation argument's unsettling possibility that quantum indeterminacy is just rendering lag in some alien computer. These aren't thought experiments, they're competing visions of reality, each with mathematical clout and existential stakes. And the wildest part, we're just scratching the surface. Every breakthrough, from quantum computers mimicking wormholes to lab-grown black holes, hints that today's wildest theories might be tomorrow's textbook chapters. But here's the real kicker: quantum fields refuse to fit neatly into any single theory. They taunt us with unanswered questions. Why do virtual particles defy energy conservation? What breathes fire into the equations of quantum field theory to make a universe? Each discovery peels back a layer, only to reveal deeper mysteries beneath. The more we learn, the clearer it becomes. We're not just uncovering the universe's secrets, we're learning how little we truly understand. So, which theory shattered your reality? The spine-tingling idea that black holes might encode our universe like a cosmic DVD. The gut-punch realization that everything you know could vanish in a bubble of true vacuum. Or the brain twist that you and this video might be lines of code in an unfathomable simulation. Drop your mind-blown reactions in the comments, smash that subscribe button and buckle up. Because if history's taught us anything, the quantum frontier always has one more surprise up its sleeve, and we're just getting started.